This is my chapter on plastics design. We'll start out by talking about compression molds for thermosets. The three basic types of a closed compression mold are 1. A semi-positive or landed type, 2. A positive type, 3. A flash type. These molds are used to make plastic parts with very heavy sections, as you can see. Also, we're involved with injection molds for thermoplastics, and the three basic types of injection molds are 1. The three-plate mold with a center gate, 2. An edge gate, 3. A center gate. These molds are excellent for making parts of thermoplastic materials. You'll have to study the diagrams. With regard to transfer molds for thermosets, the three basic types of transfer molds are injection of thermoset, 2. Plunger transfer, 3. Part transfer. These molds are generally used to produce plastic parts requiring inserts in small diameters and those parts having very complicated shapes. And we talk about ejector pin marks. In order to avoid surface imperfections caused by gates and injector pins, the drawing should specify those areas which are not to be marred. Warpage allowance. One method to assure the best results for a finished product is to indicate warpage direction and allowance on the drawing. Long, flat strips. If warpage is not permissible on a long, flat surface, ribs should be added. Sink marks. One method to reduce the possibility of developing sink marks in thermoplastic parts is to make the thickness of adjacent walls and ribs thinner. Adjacent walls should be about 60% of the main wall. Tapping in plastics. When molding holes to be tapped or for having molds molded in threads, the hole should be countersunk to avoid chipping. Sharp edges. There should be no sharp edges on plastic parts to prevent the possibility of chipping. Inserts. An excellent method for securing an insert is by hot rolling the plastic over the insert. Insert with tight tolerances. Tight tolerances, for example, plus or minus 1,000, held with maximum TIR of 3,000, can be held by using the inside or outside diameter of the insert. In most cases, assembling inserts into a premolded hole is preferred. This technique reduces the possibility of plastics flowing over metal surfaces and prevents the scratching of plated inserts during flash removal. All inserts, regardless of method of assembly, should be surrounded with reasonably thick plastic, since thin walls can crack and also show sink marks. Here I talk about critical tapered openings and projections. Ordinarily, on a plastic part drawing, it is adequate to specify a particular degree of taper. However, if a tapered projection or opening is critical, the following method of dimensioning is acceptable. In the case of a living hinge, very often plastic is molded, coined, or cold formed to create a living hinge. As illustrated, the cover, hinge, and box were molded as a single unit. There could be a mismatch. Actually, it may be preferred. When the misalignment of two molded parts appear, it is called a mismatch. This is usually due to shrinkage problems or to warpage of a part. Often a mismatch is designed into the part so as to make their appearance less objectionable. With regard to hinge pin design, I show designs which require the drilling of holes or the use of cams in the design. On this page I show a hinge pin design with no cams. In a similar hinge design, there is no need for drilling or cams in the mold. Drive pins and self-tapping screws. Metals as well as plastics can be assembled to plastic parts using drive pins and self-tapping screws. Another method is hot stake or press. This method can be employed to attach metal, glass, leather, etc. to plastics. You can also have a sonic welding of plastics. This method of assembling plastics to plastics is widely used. It is especially suited to joining hard plastics. With proper fixturing, the process can be fast and inexpensive. However, particular attention must be paid to the design of joints. Cementing. The use of solvent cements, epoxy, etc. must be carefully considered. You'll have to consult with the molder. Engraving and stamping. Raised letters can be molded on plastic parts by the engraving and stamping of molds. In order to have depressed lettering on a molded part, there must be removable engraved metal pads inserted into the mold, and the depressed lettering can be filled with ink or paint. Another technique for decorating flat surfaces is by means of silk screening and hot stamping processes. On this page I discuss draft for molds. Many factors determine the draft of a mold, such as type of material, surface area, length of draw, and method of ejection. Ordinarily, the draft may vary from 0.25 to 4 inches. In special cases, a no draft condition may even be possible. Also discussed is wall thickness. In order to prevent uneven shrinkage causing internal stresses, the walls of a plastic molded part should have a uniform wall thickness. The minimum wall thickness of an injection molded part should be 50 thousandths of an inch. The minimum wall of a compression or transfer molded part should be 0.0625, 16th of an inch. Ribs. A preferred method for designing ribs is shown on this page. Also, molded bosses. The height of bosses should be kept to a minimum to prevent the trapping of gases and weakening of the boss. If 4 bosses are being used to mount a component, it will probably be necessary to machine one of them in order to achieve a flat surface. On the other hand, if 3 bosses are used, machining may not be necessary. On page 10 here I discuss holes in plastic parts. In order to facilitate the removal of a part from a mold, holes should be designed perpendicular to the parting line. It is not advisable to mold 2 holes at right angles to each other. The hole perpendicular to the parting line should be molded and the side hole should be drilled. Holes which are difficult to mold should be drilled, for example holes under a 16th inch diameter. Sometimes it is not feasible to mold very long, slender holes. In such cases, it is advisable to mold only a portion of the hole and drill the remainder. It is always preferable to mold through holes rather than blind holes. The molding of through holes is easier because core pins can usually be supported at both ends. Holes larger than a 16th diameter should not be deeper than twice their diameter. Regarding inserts in plastic molded parts, inserts should always be placed on the same side of the parting line and at right angles to it. Also, there should be adequate clearance between the insert and the neighboring hole and between the insert and the edge of the part as tabulated, as shown. All inserts should have diamond knurling when subjected to both tension and torsion. On this page, I talk about structural foam. In general, structural foams are preferred when designing large, complex, rigid shapes, such as housings for mechanical and electrical components. These moldings are extremely light and rigid, and the cellular core provides improved thermal insulation and noise attenuating qualities. The structural foam process. The process is similar to injection molding, and the foam is obtained by using either of the following techniques. A, by introducing inert gas directly into the melt, and B, by pre-blending the resin with a chemical blowing agent, which when heated causes inert gas to be released, which disperses through the polymer melt. In either case, the gas-resin mixture is forced into the mold cavity under pressure, and the mold is filled as the gas expands with the material. At the mold face, a tough external skin is produced which covers a rigid internal cellular core. Applications for this type would include, typical applications would be, structural foam includes computer panels, drive frames, complex doors, mounts for instruments and latching mechanisms, molded one-piece card cages, card guides with zero draft, and so forth. Structural foam offers greater design freedom than is possible with metal and at a much lower cost. In order to avoid difficulties in molding, grill work and slotted areas should be located perpendicular to the flow of the material in the mold. If perpendicular orientation is not possible, a flow runner across the back is advisable. On this page I talk about ribs. Whenever it is necessary to increase the rigidity of a part, ribs are preferred to thick sections. Intricate ribbing can be designed on the back side of large appearance surfaces, because structural foam allows a part to be free of sink marks. For proper rib design, the base must not be too thick, nor the tip too thin. Bosses. On structural foam parts, bosses are easily designed to accept fasteners and support components. When there are heavy loads on bosses, they should have adjacent walls and ribs for support. Also, these bosses should be provided with generous fillets. With regard to wall thickness, structural foam provides greater rigidity in large parts than is possible with ordinary injection molding, because the normal wall thickness is 1/4 of an inch. For special applications, the 1/4 inch wall can be increased. Wall thickness of less than 1/4 of an inch is not recommended because part stiffness would be reduced. Also, a thinner wall tends to increase molding problems such as warpage, unfilled parts, and sink marks. A uniform wall thickness is preferred, as in the case of injection molded parts. Varying wall thickness without sink marks and stresses is possible, however, if the transition from thick to thin walls is smooth and generous radii are provided. Inserts in general. A variety of metal inserts are available for use in standard foam, structural foam products. Threaded fasteners are used successfully for repeated assembly and disassembly of parts, and can provide higher pull-out strength than can be obtained with self-tapping screws. The method of installing inserts can be done by ultrasonic welding, press fits, or molding in inserts. Fillets and radii. As an aid in filling the mold and to reduce stress concentration on inside and outside corners, the largest possible radii should be used. The optimum fillet and radii for 1/4 of an inch wall is 0.15 inches radius, but a 0.125 or 1/8 radius is acceptable. However, the radii should not be less than 1/16 of an inch. Draft angles. Generally, a draft angle of 0.5 to 3 inches is adequate to release a part from a mold. In certain situations, a draft angle of 0 inches is possible. For example, if molded one-piece card cages or as outside ribs. Fabrication. For simple testing and appearance, parts can be fabricated from structural foam panels, which can be readily purchased. Such panels can be cut, machined, and bonded to produce samples at the lowest cost. Molds. Small numbers of actual parts can be molded in structural foam by making low-cost molds made of epoxy, kirksite, or cast aluminum. The epoxy mold is suitable for producing from 1 to 25 parts, whereas the kirksite or cast aluminum molds are adequate for limited production. Self-tapping fasteners. The compressible cellular core of structural foam allows for the satisfactory use of self-tapping fasteners. In this application, thread rolling screws are preferable to the thread cutting variety. In order to maximize performance, cord holes should be molded. We'll start this page by discussing ultrasonic inserts. Repeated assembly and disassembly of parts is best achieved by use of the ultrasonic insert. Whenever possible, the holes used to accommodate these inserts should be molded into the part. Drilled holes can be used but are not as reliable as molded holes. The manufacturer of such inserts should be consulted for the proper hole geometry. Expansion inserts. The principal advantage of this insert is that it is cheaper than the ultrasonic insert. They are placed in preformed holes, and when the screw is installed, the insert expands against the side of the hole to retain it in place. The proper use of expansion inserts in structural foam requires consideration of the following factors. 1. A boss diameter should be at least 2 times the diameter of the insert. 2. The insert, and not the plastic, should carry the load when designing component parts for clearance. 3. If a final assembly procedure required any sort of heating cycle, the heat can possibly loosen the insert from the foam. There are several ways for ultrasonic bonding. 1 is staking. Staking is the process of melting and forming a portion of a plastic stud in order to retain another part, as shown. Spot welding. It is the process of creating small localized bonds between 2 parts of structural foam. Vibration welding. Vibration welding of structural foam parts is capable of producing strong pressure-tight joints. The process is especially suitable for parts that require permanent loads over large areas. Solvent bonding is also possible for bonding structural foam parts to each other. In some cases, other plastic parts may even be solvent bonded to foam. With regard to adhesive bonding, it has many applications, such as cementing structural foam resins to themselves, to other plastics, and to brass, aluminum, and steel, etc. On this page I discuss rim molding, which is reaction injection molding. It is a production method which results in a product made of polyurethane structural foam. When molded, this material results in a component with integral solid skin and a low density microcellular core. Polyurethane allows designs of greater versatility than is possible with the usual materials and methods of production. The wall thickness can vary from a minimum of 1/4 up to 1 inch. However, when the geometry of a part requires a variation in wall thickness, the transition should be gradual and generously reduced in order to provide a better flow of material. As a rule, wall thicknesses between 3/8 and 1/2 inches are most desirable. A thicker wall increases cycle time, and a thinner wall may result in improper fill and poorly formed parts. Radii. Every effort should be made to eliminate sharp edges on a part. A minimum radius of 1/8 inch is advisable in all cases. Otherwise, there is the possibility of air entrapment and damage to the outer skin. If the outside wall of a part is less than 8 inch high and a no-draft condition is possible, if more than 8 inch high, the outside walls of the mold should be removable. Nevertheless, it is always advisable to design parts with a taper of at least 1.5 inches. Otherwise, it's likely to be difficult to demold the part. With regard to undercuts, undercuts should be avoided so that in production of a simple two-piece mold can be used. If undercuts are a necessity, automatic side pulls must be built into the mold, thereby increasing overall cost. On this page I discuss cutouts or holes. The same rules which apply to undercuts apply as well to cutouts. Inserts and pulls may be necessary. Occasionally, if the parting line is chosen widely, there can be cutouts even though a two-part mold is contemplated, as shown below. Bosses. Molded-in bosses are used to provide for assembly of components. A boss should not have an excessively thick cross-section. The ideal should be half the OD with a minimum of 1/4 inch wall thickness. Bosses should be attached to the outer wall of a part to prevent air pockets from developing during the molding process. If this is not feasible and a boss must stand alone, the taper of the boss should be as large as possible. Cross ribbing. One method of stiffening the flat side wall of a housing is by means of cross ribbing as shown. However, it must be remembered that the simpler the design, the less expensive it will be to produce. It is not advisable to just throw in ribs because it looks like they ought to be there. However, if there is doubt that the part will be stiff enough without ribs, a properly designed part can be of benefit. Generally, excessively thick cross-sections of a rib should be avoided. In addition, properly designed ribs can maintain minimum part weight and cycle time, whereas an increased wall thickness adds weight and may increase the cooling time of the part.